Let's wait for a few minutes to see if anyone else joins.
Yes, sir.
Is my screen visible?
Yes, sir.
Okay. Okay, so let's get started. Uh, so last week we discussed about the kinematics of the manipulators and how we can get the relation between joint space velocities, that is the joint rates, and the end effector velocities, that is in the task space. So we got ourselves familiarized with the concept of Jacobians and what role do they play in the kinematic analysis of manipulators. Then we saw about singularities, how they are related to Jacobians. We saw that the joint angles at which determinant of the Jacobian goes to zero, those are the configurations in which we say that the robot is at a singular configuration and it loses a certain number of degrees of freedom. And then we also solved a few questions, and we saw that for a 2-hour manipulator, indeed, how joint rates are related to the end effector velocities through the Jacobian. So, continuing on the same topic, but now moving on to uh, deriving few relations which are very crucial while doing kinematic and dynamic analysis. That is, in a system having multiple links, how do we basically do the find out the velocities from one link to another velocity of the other link, and similarly how to do static analysis if forces are and moments are known at a link, then how to propagate it to other links in the kinematic chain, right? So let's get started. Okay, so what we will first see is velocity propagation, and the other part is forces propagation. Here propagation means propagating along the kinematic chain. Kinematic chain and propagation along it. Right, so let's have a look at this figure.
Sir. Sir.
Yeah, go on.
In general, sir, in simple terms, sir, propagation means movement along a particular direction, sir.
Yeah. The usual meaning of word is the same. That's it. So
Okay, the
basically,
space
what,
propagation.
yeah, so basically, propagating here means that we know the values of velocities, let's say at the end effector, and we know some angular rates. Then, how do we basically using that value? How do we find the values of the subsequent links in the chain down below, up till the base? So basically, we are propagating the values. So sequentially, we will be calculating. We will come on to a relation which relates the velocities in of the one link in the previous link, let's say, or from one link to the next link. So that's how in that chain, once you start from, let's say there are three links, So starting from the third link to the second link to the first link, which is again connected to the base frame. So that's how we, I would say, propagate the velocity uh, up and down the kinematic chain, and similarly the forces. So that's why this term is generally used in books and all. So I am borrowing from there itself, right? So let me just talk about this figure. Uh, these are two links you see in this figure, and there is a revolute joint. Uh, this is a revolute joint, right? And the axis, as you know, as per DH parameter, the z axis of the I plus 1th joint is marked along the axis of the revolute joint. And yeah, so this is the ith link, and this is the I plus 1th link, right? And this vector, which I will highlight, so this red vector, right, this is this quantity, and what this denotes is the, now this point is the origin of the I plus 1th frame, right? So as you would remember, in the first thing that we do while analyzing any kinematic chain of links is that we assign frames. So this is the origin of the I plus 1th frame, which is at the point where I plus 1th link is joined to the ith link, and this P of I plus 1 is the position of the position of the origin of the I plus 1th frame, and the subscript and the superscript on the left hand side, right? So basically a notation like this here means that position of the origin of the I plus 1th frame expressed or with respect to the ith frame, right? So let me write this. The first quantity which you see here is this, right, which is the position of the, which point, the origin of what, origin of the I plus 1th frame with respect to the ith frame. So this quantity is expressed in the ith frame. This quantity, like written like this, is expressed in the ith frame. Okay, so that's the first quantity of interest here. The second is this one. So now that you are familiar with what the subscript means and what the superscript means, so subscript is the, again, the the velocity or the position of which frame we are writing, and the superscript on the left hand side denotes with respect to or in which frame we are expressing that quantity. So similarly, this this is the velocity, or I should specify the linear velocity, right, of the origin of the I plus 1th frame expressed in the I plus 1th frame itself. Okay. So now please note here is that this is the absolute velocity of the I plus 1th frame, right? And it is expressed in the I plus 1th frame. So there are two concepts here which are slightly like sometimes gets confusing. One thing is that if I want to express the velocity of point A with respect to point B, right? So let me just take an example. So because while working with, since there are multiple frames here and you would be working with these frames, it's better to make things clear, right? So let's say this is frame A and this is frame B, right? And there is also a O, which is the ground frame, or the ICS. What is ICS? Inertial coordinate system, which is fixed. Also we can denote by putting two as a slash marks like this. So this shows that this frame is fixed, right? Now this is the position vector to the origin of the A frame. This is the position vector to the origin of the B frame, right? So this is R A and this is R P, right? And so this is a vector. RA and RB is a vector. When we write RA and RB here, we means it's a vector from the origin, that is of frame O, to the origin of frame A, that is RA, and the second one is the vector from origin of frame O to origin of frame B, which is RB, right? Now this vector RB can be expressed in different frames, right? So the same vector RB, right? Let's say RB is in the O frame, right? Is expressed by some maybe XB, YB, ZB, right? Now the same vector, physically it's the same vector, can be expressed in, let's say, the A frame, right? Then it will be some other values, you know. And similarly it can be expressed in the B frame. Then it will be yet another set of values depending on how these frames are oriented, translated with respect to each other. So the point which I'm trying to make is that the vector remains the same. The vector is, what's the physical quantity this vector is representing? It's the position vector from the origin of frame O to origin of frame B, right? So physical quantity remains the same. Once you are writing some, it's a frame independent representation, right? There is no frame associated to this piece of information. But once we are, let's say, using this vector in some equation and we want to write out its components, right? Whenever we start writing out the components, then we need to decide upon in which frame we need to write these vectors, right? And that's our choice, right? We can write in any frame. Usually we choose such frames which are convenient to us, right? Or some frame of interest in which we want to find some quantities, right? So the idea is the same RB vector can be expressed in the O frame, in the A frame, in the B frame, and the components, the individual components, those values would differ, right? So similarly here, this V of I plus 1, that is the velocity of the origin of the I plus 1th frame, is the velocity with respect to the inertial frame, right? The quantity is fixed here. that it's the velocity with respect to the inertial frame. It's the absolute velocity of that frame. It's not with related. It's not relative to some other moving frame, right? But this velocity vector is, the components are being expressed in I plus 1th frame. So that's what this denotes. This superscript on the left hand side, right? That's what it denotes. So this is the quantity, right? This is the quantity, and this is its description in which frame it. This is the description. So this is the description frame, and this is the quantity, right? So from now on, please keep in mind this crucial distinction, that what's the physical quantity and what's the frame in which it is being described. So because I am explaining this because a doubt might creep in that this means velocity of I plus 1th frame in the I plus 1th frame. Then if you are sitting on a link and you are trying to see its velocity, then since it's a rigid body, the velocity would come out to be 0, right? But that's not the quantity we are discussing here. The quantity is velocity of the origin of the I plus 1th frame with respect to the inertial frame. That is, we are talking about the absolute velocity of the origin of the I plus 1th frame, and that vector, that velocity vector, is being described in the I plus 1th frame if we write like this. Okay, so moving on to oops. This is a little weird here. Sorry for this. Just wanted to arrange the things. Oh, still not. Yeah, it's there. Got it. So now, once we have that out of the way and we understand the notations, let's go back to the actual physics. So I believe you would have some exposure to dynamics and kinematics of rigid bodies, and a very basic relation there is that, let's say there is a rod, right, and it's rotating with some angular velocity omega, right, and there's a point here A, and this is the hinge point, and this is the position vector from this O point to A point, so OA, right? So the linear velocity, right, the linear velocity VA is omega cross ROA, right? I think everyone is familiar with this relation, that the linear velocity of a point on the rotating body is omega cross the position vector of that point, right? So now in this case, what's special is that point O is fixed, it's not moving, right? Now in case I also add one more layer to this problem or to this system is that let's say there is a cart, right? So the cart is moving with certain velocity v c. This is the cart, right? So this frame, the c frame, is now moving, and here is the same link again mounted on this, which is rotating angular velocity omega, and here is the point of interest a, right? So again, now here is, let's say, point c, and now our inertial frame is not on the cart, right? Because the cart is moving. So let's draw the inertial frame here, right? Which is the inertial frame ICS, right? So now what? Now if I am sitting on the cart, right? If I am sitting on the cart, I see only rotation of the rod, right? I If I am on the cart, I see that the rod is only rotating, right? So how can we write that mathematically? That velocity of point A with, let me fix the notations here. Yeah. So velocity of point A with respect to point C, right? Here it is with respect to O, and I will write here also like this. So this is position vector of point A from point O, right? So this is, yeah, so what the other quantity that we are writing right now? Velocity of A with respect to C, right? And this quantity, so we are not on the inertial frame, we are sitting on the cart itself, right? And the rod is just rotating with respect to the cart. So the velocity can be again using the previous relation written as omega cross. Now the r here, point to note here, the r will be, since we are sitting on the c frame, it will be a with respect to c, right? So that is the velocity of a with respect to c. Now what is velocity of a with respect to O, right? Which is the inertial coordinate system, because usually we are interested to find the absolute velocity, right? Not relative to some moving frame. So we have seen that it is given that velocity of C with respect to the inertial frame is Vc, right? Let's say if we constrain that the cart is only moving in the x direction, so let's say it is some v I cap, right? Vc I cap, this is the vector, right? So as you would think now, how do we write the velocity of point A with respect to the inertial frame, that is A with respect to O, it is A with respect to C plus C with respect to O, right? And what are these quantities? So I will first write VC, because generally it's written like that, and omega cross R A C, right? So this is the important relation which we were looking for. Like, I will come exactly the form for manipulators, but right now this is the relation. What does it tell is that the absolute velocity of a point which is both like rotating and translating, right? Because when you sit on the inertial frame, this rod is not only rotating but it's also translating, right? So it will have both velocity due to the translation and due to rotation. So that's how we proceed, right? We write the velocity with respect to the intermediate frame, and then we write the velocity of the intermediate frame with respect to the inertial frame, right? So this is the linear velocity due to rotation, right? And this is linear velocity due to translation, right? Okay. So similar concept we will apply also for our analysis of kinematic chains, right?
Sir,
Yes, Karthik.
sir, to include rotation, we wrote omega times r, sir.
Yeah, omega
R.
cross R, yes.
Just to
Cross
include
product of two
rotation.
vectors.
Okay, okay. Just to include rotation, we have written that quantity.
Yeah. As I
To
mentioned,
write the
like,
overall.
yeah, so if you sit on the cart itself, right, you would see the rod to be just rotating about the axis, this axis, right? Because you are sitting and you are moving at the same speed as the cart, right? So you would not see the rod as translating, right? You would just see rotating. So in the C frame, the point A has a velocity of omega cross RAC, right? So that is the velocity of point A due to the rotation part. Like, it's just the way of approaching the breaking down the solution, right? And then what we do is that, okay, now let's jump to the inertial frame, and now the C frame itself is moving with the velocity of VC, right? So let's add that velocity to the velocity of A with respect to the C frame, right? So basically, and this is how you can do this sequentially. You can basically stack up the frames and keep on adding velocities of the frames before, right? So some this something similar we will do here there also. So we started from the point of interest and we went backwards to the inertial frame to find out the velocity of the point of interest with respect to the inertial frame, right? So this is in some ways also a propagation, that we first wrote the very first frame, right, in which the motion is very simple, that it's a rotation about a fixed axis in the C frame. We wrote omega cross RAC. Then once we have it, so now we move from C frame to the O frame, and there we see that the C frame also has a velocity VC. So add on to that velocity. If there would have been one more frame, right, after O also, let's say that was the inertial frame, then we would jump onto that, right? Let's say the P frame, and in that add the velocity of the O frame. So similarly, we can just keep on jumping from frame to frame and adding velocity of the origin of that frame, right?
Sir, when we jump from C frame to ICS frame, sir,
Yeah.
at that time, is that rod moving, sir? A rod, I mean CA rod, is that moving? Is
Yeah.
that
It's
rotating?
it's moving. It's moving.
It's moving. Okay.
Yeah.
It is not stationary. We didn't consider it as stationary, so that rod.
No,
It
no,
didn't
no,
stop
no,
rotating.
no,
It
no.
is rotating.
So when we move from C to O, now our point of interest is what's the velocity of C with respect to O. because we already know what's the velocity of A with respect to C, right? So I know that if I am at C, the rod point A is having velocity of, let's say, 5 meter per second, right? Just a very crude example, right? Now, if I jump from C to A, right, then I have to see, sorry, C to O, then I have to see what's the velocity of C with respect to O, which is actually the inertial frame, and thus just add on that velocity to the velocity of A, which we already calculated. And in the, yeah, and in the entire this it's just a process of analysis. In reality, if such a system would exist, there is no need that we are stopping something and then moving it. The system is continuously moving ahead, rotating, whatever it's doing, right?
Yes, sir. Got it, sir.
Okay. So in a way, I also described how velocities are calculated here also, right? If there are, so basically here is the I plus 1th frame, right? And I plus 1th frame is at a distance of this p I plus 1 from the origin of the ith frame, right? So now what we assume here is that, so we want to find a relation between the velocity of the ith frame, origin of the ith frame, which we assume that we know, right? Because again, we would start from the base and move outwards, right? So velocity of the ith frame we know, right? So given that, what's the velocity of the I plus 1th frame? So that's the same thing, right? Here is the one frame whose velocity is known. So that velocity plus the velocity of the origin of I plus 1th frame in the ith frame, which is just a rotation of, by this whatever the angular rate of this joint into the distance between these two frames, right? This is a pure rotation. So let me make things clear here. So let me draw multiple frames. Wait a second. Okay, so this is the O frame. So from now on, O frame, I would, whenever I would draw, that would be the ICS, the inertial frame, inertial coordinate system. Okay. This is frame 1. This is frame 2. This is frame 3, right? And this is the final end effector P. So you can draw frame 4, but frame 3 and frame 4, they are not moving relative to each other, right? Because they are on the same rigid body. Okay, so let's analyze from frame 2 to frame 3. Okay, so what we will have is that we have velocity of frame 2 in the second frame, right? And what we have is that the basically this vector, the position vector of origin of frame 3 expressed in the 2 frame, right? And what's the third thing that we need is the angular velocity, right? So angular velocity is, which angular velocity will affect it? The angular velocity of this joint, right? So what is the omega of the second joint expressed in the second joint, right? So the relation would be velocity of the third frame expressed in the second frame is first, right? So first write the, let's say if you are sitting on joint 2, then joint 3, the origin of joint 3 is just rotating, right? Just as it was case in this example. When you are sitting at C, point A is just rotating, pure rotation. Similarly, when you are sitting on joint 2, what you will see at about joint 3, what you will see that joint 3 is just rotating about your position, right? So it's a pure rotation. So the first component that will be is omega cross r itself. So omega, it will rotate at a rate of omega 2, and the position vector of that joint is p3 2, right? So that part is done. Now, as we did in this example, once we wrote the velocity with respect to c, we added the velocity of c itself with respect to the inertial frame, right? And here, as I mentioned, that we know that v2 is the velocity of point joint 2 with respect to the, or frame 2 with respect to the inertial, right? So that's how we get the velocity of 3 with respect to inertial. So this is the absolute velocity of 3, right? This is the absolute velocity of 3. This is the absolute velocity of 2, and this is the relative velocity part. This is the relative velocity of 3 with respect to 2, right? So again, a very fundamental relation that we used to study in our schools also, that velocity of b is velocity of a plus velocity of b relative to a, right? So the same thing is happening here also, just that we are writing explicitly what is velocity of the relative velocity part, which is omega cross r. Any doubts in this expression?
Sir, it should be V3 superscript 3, no, sir? For absolute value of 3, you have written that. Absolute velocity of 3 in that equation.
No,
It
no, no,
is
not
V.
necessary, not necessary. As I mentioned, Karthik, that the subscript, the superscripts in all these vectors, right? It's just a matter of choice, right? The physical quantity which is being written is the same. So, I mean, I took this notation from the book itself, but you know, there's no need to write that also. This equation is also perfectly fine, right? And I would, just to make things clear, like this. So the superscripts of 2 that you see everywhere, that is just that while actually calculating this quantity, the components are expressed in the frame 2. Okay, the quantity itself is the absolute velocity of 3, that v3, the way we have written v3, because what we are doing, we are adding to absolute velocity of 2 the relative part of between 2 to 3, right? So it's not that if I give superscript here 2, then it's relative, and if I give superscript here 3, it's not it's not I mean, yeah. So the superscript here does not change what quantity you are writing, right? So if I go back here, what did I mention? That the quantity is this thing, v of I plus 1. That's the quantity we are writing, right? And the superscript is just a matter of choice, right? It, and we can easily transform from one to another. We can write in I plus 1, we can write in I, we can write in I minus 1. That would not change that this is still, and if we use this relation, that will still be the absolute velocity of I plus 1, or in this case 3, right? Because that's how we have calculated it physically. Physically, what does this relation mean? That we have the absolute velocity of 2, that is, we know with respect to the inertial frame how fast 2 is going, right? And once, so that part, that is one part. And when we sit on 2, how fast 3 is going with respect to 2. And if we add these two, what do we get? How fast 3 is going with respect to the inertial, right?
Yes, sir.
Right.
Yes, sir.
So
Clear, sir.
so
Yes,
basically
sir.
the physical relation is just this. After that, all the other things that you see are the mathematical constructs that in order to, let's say you are actually solving for this, then any vector, right, any vector you would have to write in some frame, right? So again, coming back to very fundamental concept, that if I just write a vector v, right, this inherently does not say in which frame it is being written. It just says that it's a vector quantity v, and it might be some physical meaning, let's say velocity of a ball, right? So this does not carry any information about frame. So if I ask you to write a vector v and write its components, then you should ask me in which frame, right? So very important difference you should always remember. If I just ask you to write a vector v and not ask about its components, then you need not care about frames. Once I ask about its components, that v is a velocity in 3D space, and it's being expressed like vx, vy, and vz, then the question comes like this: vx, vy, z, vz are the components when v is expressed in which frame. Now it could be inertial frame, it could be some other moving frame, like any frame which you take. So that's what it is happening here. As I would just show you next, is that the same equation, right? Here we have everything written in the second frame, right? The same equation we can just multiply by a rotation matrix on both sides, and the same equation everything will be there in the third frame, because the relation between, so now since you have pointed this out, this, that is the absolute velocity of joint 3 in the third frame, is, how do we transform from this, is that we multiply by the appropriate rotation matrix. That's it, right? So multiplying by rotation matrix will not change the magnitude of the velocity vector, right? Neither it will change the direction. It will just change what are the actual values of the components of this vector, right? So again, physically, let's say if in let's say the physically the velocity of, let's say velocity of this frame comes out to be like this, right? So it's not that physically this vector remains the same, no, because the velocity is not changing. Once you, let's say I freeze the mechanism at this moment, the velocity is the same. The only thing is that if I write its components in frame 3, the components would be something else. If I write the components in frame 2, it will be something else. If I write in frame 0, the components will be something else, right? So that's the only difference. So frames create a difference in the value of the components, not the actual physical quantity which the vector is intended to represent. Okay.
Yes, sir.
Like I'm reiterating this again because it's a very crucial difference, and these notations sometimes make things confusing. So it's very important that we are clear on what is the physical quantity we are expressing, and again, while solving or while finding values, what are the frames which are using. Okay. So yeah, so I also showed you that how to convert from the description of the velocity in one frame to the other frame, because frame 2 and frame 3 they are, what's the relation between these two frames, frame 2 and frame 3? They are translated by some distance L2, right? And there is some rotation angle between them, right, which is theta, what this is, if this is theta 1, this will be theta 2, and this will be theta 3, right? So frame 2 and frame 3, so frame 3, how do we get, we translate frame 2 by L2 and rotate by theta 3. right? That's the relation between 3 and 2. And when you are transforming velocities, right, so you one question should come to your mind, that why didn't the translation part come here, when transforming? Because this distance is fixed, right? This distance is fixed, L2 is not changing. So this velocity, there is no linear velocity between 2 and 3. There is only velocity due to rotation, right? So the only transformation that would come here is that the only transformation that we would need to go back to frame 2 is that we need to rotate by theta 3, and that would again give us the velocity in frame 2 or frame 3, vice versa.
Sir,
Mm-hmm.
I understood this topic, sir. I
Mm-hmm.
mean, what you have explained so far.
Mm-hmm.
Just a small thing, clarification.
Mm-hmm.
Here, P3 superscript 2 you have written, no, sir. In
Mm-hmm.
place of that, if we had written P2 superscript 2, then those two will be equal, sir.
No, 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 no.
No, it
If
won't
you
be.
are saying that you want to write P2 and in
Superscript
2,
2.
right?
Yes,
This
sir.
quantity.
Yes, yes,
Yeah.
yes, yes.
So as we have established our notations, the subscript, right? The thing here down below. This is the this is the frame of whose origin we are writing the position vector to. So you are changing the frame itself, right? The point itself, basically, the point to which the position vector points, right? So
But sir, it is distance, no, sir. Distance between frame 2 and frame 3, no, sir. So even then we can't write, sir.
no, 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 right? So
In distance, okay.
yeah, I would explain what this notation would mean. So the way we have established the notation here, specifically in this case, is that the pi plus 1 is the position vector from ith frame to the I plus 1th frame, right? Agreed?
Yes, sir.
That's how we have defined it. So if we write p2, then it would denote the position vector from the, so this would basically, this would be our I plus 1, right? So if we write
Yes.
p2, then I is 1, right? So this will denote the position vector from this first frame to the second frame. This is p2. So this is the actual physical quantity p2, and the superscript 2 will mean that it is expressed in the second frame.
Okay.
So
Okay.
yeah, so you should remember this convention, the in the initial figure which I showed, p I plus 1 and expressed in I. So if you see the definition, the position of the origin of I plus 1th frame, right, with respect to ith frame. So P3 is position of 3 third frame origin with respect to second frame. P2 will be position of second frame origin with respect to the first frame, right, and so on.
Yes, sir. Yes, sir. It is clear, sir.
Okay. All right. So so this is how we calculated the linear velocity, right? Now in the calculation of linear velocity, a quantity came which is the angular velocity, right? And angular velocity is also, every joint has its own rate, right? So first link is moving, let's say, at 5 radian per second, second link is moving at 2 radian per second, third link is moving at 2 radian per second, let's say. So what's the absolute, or what's the angular velocity of the third link, right? So just say, thinking intuitively, if all the axis of rotation are all the same and parallel, then it would just be addition. You can just add the angular velocities, and basically that's it. If the axes are parallel, if the axes are not parallel, we have to just rotate it accordingly while moving from one frame to another. So for angular velocity, right? So again I will write in the I notation. So as I write, I would suggest that you know just think in your mind what this quantity is representing based on the discussion that we just concluded, what all these notations are meaning. So I will first write it, then I will explain. So all these notations and diagrams which I have taken, so let me just put the reference. The reference is Intro to Robotics book by J. Craig and third edition. Okay, so interested students can further read from this. It is explained very well, same concepts in the book. So basically, what's the quantity on the left hand side? It's the angular velocity of the I plus 1th joint, right? I plus 1th joint, and expressed in the I plus 1th frame, right? So here you would see everything is expressed in the I plus 1th frame. Everything is in I plus 1th. So this thing you have to keep in mind, that when you write equations which are in which you are also writing about in which frame they are being described, then on both sides the frame should be consistent. Like each quantity should be expressed in the same frame, right? So that's the beauty of frame independent equations which I wrote here, right? So they just, this is frame independent, right? They just eliminate some bookkeeping, at least in understanding phase, that okay, this is the physical relation. Now while solving problems or while implementing, I would in fact have to choose a frame in which I have to express these vectors, which is this one. So this is frame dependent. This is a frame dependent equation because it is written in, especially in frame, specifically in frame 2, and on both sides each quantity is expressed in frame 2 itself, right? So similarly here each quantity is expressed in I plus 1th frame itself. So if I write for the above example, so omega 3 expressed in 3, that is angular velocity of the third joint expressed in the third joint itself. It is, now what I have to do, that I know angular velocity of 2 into angular velocity of joint 2 expressed in second frame, and now I transform from second frame to the third frame by multiplying with the rotation matrix, just like we did here, right? And then, so this is basically the first term is what's the angular velocity due to each of the preceding links, the preceding link, because they are rotating. If joint 3 is not rotating also, then also there would be some angular velocity, right? Let's say if theta of that joint is 0, right? It's not rotating, then also there would be some angular velocity because the previous links are rotating. So that is that component, plus the additional component due to the rotation of that joint, right? And the axis of that rotation is along z of that frame, right? So this is it. Basically what we are doing is that the frame 3, angular velocity of frame 3 is the angular velocity of that joint, right? Angular velocity of that frame, this is that quantity, and the angular velocity of the previous frame, right? So that's how we add the angular velocities up to get the propagate the angular velocities, right? So what I would suggest is to take up get this book and solve some examples from there to know, understand better. Okay, now, so while doing kinematics, these are the two quantities which we are interested in, right? The angular velocity and the linear velocity. And for both, we found out the relations of propagation. All right. Okay. Now, the next thing is, so that sums up the kinematics. Now let's come on to statics. Right. So again, by statics I mean that, there is a manipulator and it's not moving. It's in basically static equilibrium. It's locked. The joints are locked. Of course, to keep it in this configuration, and if there is gravity, right, it would have to apply some torque here, right? Some torque here, tau 1, some torque here, tau 2. Okay, so this tau 1, tau 2, it's applying to keep in that configuration, right? And let's say if I apply a force here, you know so for now what we will do is that we will ignore gravity, right? Gravity is not there. So what we will do is that, let's say we apply force here on the end effector, then what are the joint torques that come? Okay, so what's the relation between, so relation between forces and joint torques and propagation of forces and moments is torque itself, for static case. All right, so static case means that the links are not moving. Okay. All right, so now for this, the figure again we refer back to here, so refer figure 511, refer figure 511 above.
Sir,
Yeah.
here, sir, in this case,
Mm-hmm.
we have ignored the gravity, no, sir.
Mm-hmm. Yeah.
So,
Yeah.
so here, the torque tau 1 and tau 2 are the moments which we are applying, sir, physically. They are not generated by F, no, sir.
Yeah, so both will be the case. Like, if if I apply some forces, some torque would be generated because they would move, right? So because let's say if this is the point of application of force, right, and if I this is a distance from this joint, right, the r, so some torque will be generated, right, r cross f. So it's basically a sort of a instantaneous kind of an analysis. It's of course, in reality, if you apply a force and there is no there is no resistance from there, then due to the applied torque, the link will move, right?
Yes, sir.
Yes. So what you can imagine in this case is that that let's say if we're doing it practically, then let's say there is that the basically whatever actuator or motor is there at the joint, it's resisting that kind of a force. So basically what you can think is that it's like this, and if I apply some force, some torque, the torques here would increase from some baseline torque. Torques here would increase because I am applying some force here and to resist that force, right? So so basically there would be some holding torque already there. On top of it, if I apply some force, then what are the additional torques that are being generated at the joint? Did I clear your query?
Yes. So that is they are the resultant torque, sir.
Yes,
Right?
in a way. Like in this analysis, we would ignore that holding torque because that would be some baseline value, right? Which is keeping it in this configuration, right? So let's say if there is gravity also, and if I want to keep in this configuration, then just to keep in this configuration, let's say there is some fixed value. Let's say 5 Newton meter here, 10 Newton meter here. I am providing to keep in this configuration. So that is, and there is no force on the end effector. Okay. Now,
Mm.
what I am interested here in this analysis is that if I apply forces here, right? So now what happens due to this force? How this force is affecting the torques at the joints. So you can keep that 5 and 10 and 5 also in the analysis, 10 and 5 also. But if you ignore the gravity, then you can ignore 10 and 5 also. You can just analyze what if I apply, let's say, 10 Newton meter here, then what additional torque is created here, what additional torque is created here. So that's what we will see here.
Yes, sir. Got it.
Okay. So in figure 511, right? So similar notations and all are the same. So here also p I plus 1 I is the same thing. Now in the book from which I have taken the figure, this n is the torque or the moment, right? I will use tau because that's what I am familiar with or I'm used to. But just to clarify, here n means torque. So this is torque. And F is the force. Right? So N is torque, F is force. And yeah, so this is the ith frame, this is the I plus 1th frame. And there is some moment on this joint, there is some force on this joint. Right? So what we are interested is how if I apply a force on the end effector or on some joint, then how do forces propagate along the joints of the kinematic chain. Okay. All right. So as I mentioned, since we are doing static case, right? So if let's say I take this link, then if you go in the figure here, you know this link, ith link, one side it's at one end of the link it's fi being applied, and other end of the link fi plus 1 is being applied, right? So first what we'll do in any static analysis, we will first do force balance, right? Force balance and moment balance, that's what we do, right? So force balance, uh, there is some fi here, there is some fi plus 1 here, right? And these are basically two joint ends, just marking. So for static balance, and since we are talking about static case, what it should be the scenario for equilibrium, that basically this,
They should be equal.
yeah, equal, right? Okay. And so this is the frame independent equation. If you want to write in with some frame description frame, then let's say you can write like this, that expressed in ith frame, and this also expressed in ith frame, right? And again, if you know the forces on the I plus 1th joint in the I plus 1th frame itself, let's say if you have this quantity available with you, then you can easily transform it as we did before from I plus 1th to ith frame, right? So yeah, very straightforward, just force balance, equating the forces on the two ends of the link. So this, and we are done in the force balance part because we are
Sir,
yeah,
sorry, sorry,
yeah,
sorry, sir.
go.
Yeah. Sir, no matter what quantity it is, when it is the rotation matrix will remain the same, sir. Now here,
Yeah, yeah,
the
it will
difference,
remain the same. Yeah.
it will remain the same this
Yeah,
much.
because rotation matrix is a relation between two frame, and frame is not affected by what quantity we are expressing, right? Whether it be force, velocity, moment. The frames are just two set of axes which are translated and rotated. There is some translation and rotation between them, right? They are independent of what quantities we are expressing in those frames.
But when we rotate frames, these vectors also rotate, no, sir?
No, 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 no. So
They don't rotate.
again, we are
Okay.
not rotating the vector here, right? So what we are doing, again, we are going back to the same concept, that this is a vector, right? Now what we are doing is, first let's say we are expressing it in a frame like this, right? This is frame A. And second, what we are doing is, by multiplying the rotation matrix, we are expressing it in frame B, right? So the vector in itself remains the same, right? What will change,
Yes, sir.
as I mentioned, is the components, because in the A frame its component will be something like this, right? And
Yes,
in
sir.
the B frame its components will be something like this, right?
Mm-hmm.
So
Yes, sir. Yes.
what changes are the components. The vector is, we are not rotating the vector itself, we are just changing frames. And when we change frames, the components changes.
Okay. So
Because
we here
yeah, because if we change the vector itself, that's a different story. Because if we rotate the vector itself, it means that we are changing the direction in which force is being applied. But that's not usually done in these analysis, because it's in the, like the scenarios which we are seeing, we have we are given that okay, the force is being applied in this direction, right? And it's, for the whole analysis, the force is not changing its direction, the force is in that direction itself. So the vector remains the same. It's just that with frame A, it will have some components. With frame B, it will have some components.
sir, so we can't tell here that fi plus 1 is same as fi, no, sir? We can't tell that, no?
Yeah.
Here.
So this again. So
Yeah.
this is a this is a relation which is frame independent. To actually equate them, right? You would have to write both of these vectors in the same frame and then equate their components, which I wrote in the subsequent equation, this equation, that I express both of these vectors in the ith frame, right? In the same frame, both I express both of them and then I equate them.
Okay. Yes, sir. Yes.
Okay.
Yes, sir.
So up to the level of just stating the the physics of it, you can write frame independent equations, and they are very neat, very precise, and you know not confusing way of expressing the physics of the system. Once you move from physics to actually solving, getting some values, putting numbers and all those things, because then you write those vectors explicitly, you write those components explicitly. When you come to that stage, that's the stage at which you need to choose a frame. That's a choice which we, as a solver of that problem, we will make, that I will choose the ith frame, or I will choose the I plus 1th frame, or whatever, right?
Yes, sir.
Okay, so force balance is done. Next is the moment balance. So yeah, so in this figure we see that there is again a moment at this joint, a moment at this joint, right? So what we have to do basically is, right, so some moment at, okay, let me write tau itself, tau I fi, this is the point, right? And at this point some fi plus 1, these are all vectors, and there is some tau I plus 1. Okay, so what we are interested in finding out is the torque at the ith joint, right, expressed in the ith frame, right? So what will the torque at the ith joint? Okay, so torque at the ith joint will be the sum of two things, right? So first thing will be what we will call as a reaction torque, right? Reaction torque is that if I, if let's say this is fixed, if I rotate by some torque here, then since this is fixed here, it will provide me a counter torque, right? If I'm rotating, so that's the reaction torque basically. Similarly as reaction force here, right, since it's a static case. So first will be the reaction torque, so that will be the reaction torque of the torque on the joint after it, right? That is I plus 1. That is one component. The second component will be, as you would guess, is that about this point, right, a force is being applied. So whenever a force is being applied and the force is offset from the point of interest, right, and this is pi plus 1, right? So what is the torque due to that? It is again r cross f, right? So pi plus 1 cross f I plus 1 I, right? So this is the relation of the moments. Okay.
Sir, can you explain this? Like I understood that this tau I plus 1 is the reaction torque of tau I, no, sir. What about the next term, sir?
Yeah, I will explain. Yeah, so next term is that we are also additionally applying a load at this point, right? So let's, if there would be just this, just some force would, there is a rod and some force is being applied here, right? Consider this scenario only, right? Some fi plus 1 force is being applied at this point of the rod. Then what is the torque about this point, right? This is position of the point of application of the force, right, and the force itself. So tau is r cross f, right, as we have studied in our school level classes also, that tau is r cross f, right? So r is the distance or the position vector, not distance, position vector from the axis about which we are calculating a torque to the point of application of the force, right? So that is r, and f is the force itself. So in this case, the torque due to force fi plus 1 is pi plus 1 cross fi plus 1, right? So that's due to the additional force which is being applied on the joint after it, right? Because that will also, so it's basically like you are there is a rotating torque here and there is some additional force also here, some force is also here, so both of them will contribute to the torque on the previous joint. Am I clear?
Yes, sir. Like whatever force, whatever torque we are applying, that torque is the result, is the addition of resultant. Sorry, is the addition of reaction torque plus how much rotation it cost, right? I mean, how much moment it cost.
Yeah. So basically, these two things, they are separate quantities here. Both are acting on this joint. There is a torque also, right, and there is additional force also. So think, right? So these are not the result of each other. These are two distinct things. Because that what will happen is that actually I will show you now. I think it's time to solve an example, because that will make things clear, at least for this force balance thing. So basically it's that this is a 2R manipulator. Okay, you apply a force here, you just apply a force here now, and no torques here. Okay, only a force here at the first joint. Now let's just imagine or talk about the first joint, this joint. Okay, so let's just talk about this joint. Okay, I will name it. Okay, I will name it joint 2. So let's talk about joint 2. Now what's happening at joint 2? Joint 2 is just resisting the torque due to that force F, right? There is
Yes,
no
sir.
there is no moment on the end effector, right? There is no moment on the end effector. If I apply a moment on the end effector also, then it will resist both the moment M plus the torque due to the force F, right?
Okay. Yes, sir. Yes, sir.
So that's the thing, because we can apply both the things, right? I can apply a force, or I can apply a torque, or I can apply both. I can apply both force and torque, right? So that's the thing. We can apply each of them individually. So
And those individual things, both the quantities can generate torque.
yeah,
Torque.
both quantities generate torque. So
Oh.
moments will be just added as it is, and for calculating torque due to force, we take cross product with the position vector of the point of application of the force.
Yes, sir. Yes.
Right. So I think, yeah, there was some point which I was mentioning. Okay, if it comes up, I will just again discuss it. So the next thing that we will do is that let's do an example. Okay, so example is the same system which I just mentioned, and will make everything much more clear. Okay, so let me draw once again. So let's say this is the force. Okay, this is the base frame, XO, YO, right? This is theta 1, the usual notation, theta 2. Okay, so all right, now let's draw frames. So this is frame 3, then this is frame 2. It's not clear. Oh boy. Oops. Wait. Okay, so this is frame 2, and this is frame 1. And this is frame 3, right? So now frame 2 and frame 3, as we have seen before also, they are just away by a translation. There is no rotation between them, so they are effectively the same. And right, so basically F, the force that we are applying at the end effector, its description in the third frame is same as in the second frame. Okay, and since we are considering a planar system, let's let the force be Fx, Fy, and 0. Okay, so let this be the description of force in the second frame. Okay, the force which we are applying at the end effector. Now, as I mentioned, what's the joint torque at the second joint, right? Expressed in the second frame. So this will be, because as I mentioned, there is no m here, right? There is no end effector moment, there is only forces. So this will not be there, there will be only r cross f, right? So it will be, the point of application is, the length of link 2 is L2, right? This is L1, and the direction, basically this is the origin of frame 2, and this is L2 in the x2 direction. So L2 x2 cap, right, cross the force. Force is fx fy 0, right? Any doubts in this expression?
No, sir.
Okay, so let's do this cross product. So this cross product will come out to be, so this is along x, so x cross x will be 0, x cross y will be in z direction, and since this is 0, so there is nothing in the z to multiply, so there will only one non-zero component in that moment, and that will be in the z direction, which will be L2 fy, right. So basically, in short, you can write L2 fy z2, and that makes sense also, right? Because that's the axis of rotation of that joint. So that is the joint at torque at the second joint. Now what
Sir,
is, yeah.
I understood it analytically, sir. Like
Mm-hmm.
when we apply force that way, we get the moment will be in the z. That way I understood, sir. Here mathematically, sir, L2 x cap cross with fx, that is 0. I understood. X2 cap into fy, we get z, no, sir.
Mm-hmm.
So there, why you wrote it as 0, sir?
Yeah,
In
so
the
basically, let me both write both of them in the same convention. That will make it more appropriate. And so basically, this is what, fx x cap plus fy y cap plus 0 z cap, right? Now if you
yes,
just
sir.
take cross product, so x and x, they will be 0, right?
Yes,
What will
sir.
be x cross y? It will be
Z.
L2 fy z cap, right?
Yes,
And
sir.
the third term is 0 itself, so x cross z is 0. I mean, the coefficient is 0. Okay, so that's what I wrote here, right? So this is the x component, this is the y component, this is the z component, right? So this is what
Okay,
I
that's
wrote.
how we write it, sir.
Yeah,
Even okay, okay, okay.
L2
I
fy
understand.
z2 cap, z cap or z2 cap, z2 cap to be
Okay,
precise.
okay. I didn't understand. I didn't understood the notation back then, so now I understood.
Okay. Okay, so this is the moment or the torque at the second joint. Now what's the next thing which you will do is that, so now so this was the torque balance thing. Now for force balance, so this, since f is being applied here, so f will also be here also, right? Because f2 is because where's the cursor? Yeah, so from force balance, f1 is f, and f1 is this basically. So this is the first link, link 1 L1, and so this is f1, right? Because it's a static case, so the first condition will apply, right? So f1 is equal to f2, and f2 is the same end effector force, right? So that's the case. The force vector on link 1 is also the same. The thing which you have to do is we have to express it in frame 1, right, for further analysis. So here, how to convert from the f, which is now represented in frame 2 as fx fy0, and we have to convert it to frame 1. So what we will do, apply by a suitable rotation matrix. So here you see the rotation matrix thing in action. Okay, so now what's the rotation matrix from 2 to 1? The angle between this is, let's say, x1 and this is x2, right? So angle between them is theta 2, right? So the rotation matrix will be cos theta 2 minus sin theta 2, 0, sin theta 2, cos theta 2, 0, 0, 0, 1, right? And here it will be f expressed in the second frame, which is fx, fy, and 0, right? So upon multiplication, what do we get is that fx c2 minus fy s2, then fx c2 plus fx s2 plus fy c2, and finally will be 0, right? This is correct. Fx c2 minus fy s2, fx s2 plus c2 fy, right? So what we did, we just, the vector is the same, we just rotated the frame to find out the description of the f vector in the first frame, right? So you can also see that what's the magnitude of this vector? It is under root fx square plus fy square, right? What is the magnitude of this vector? If you will do the same thing, component 1 square plus component 2 square, you will see that the same thing comes up, right? So the vector itself is, it's neither being scaled, not the actual vector is being rotated. It's just that we wrote that vector in a frame which is rotated from frame 2. So the components changed. All right. So
Yes, sir.
right. So f1 is known. So now finally we can write the joint torque at the first joint, right? And that in the expressed in the first frame. So that will be first look at this expression and see if it is the same thing which you discussed, right? That the joint torque, now you, in this, for the torque at joint 1, both the terms will come due to a reaction torque of the joint torque of 2, the torque that is applied at joint 2, and the force which is there, right? So both the things are present here, both the reaction torque and the torque due to the force at the joint. So let's write it. Now note that here we are writing the joint torque at of 2 expressed in the first frame, right? But you will note that the z2 and z1 axis are the same, right? Both are pointing out of the plane, both are parallel, so there is no need to do any rotation matrix transformation here. We can just, here also we can write 0, 0, L2 Fy. Is this part clear? Why we just directly wrote like this?
Yes, sir.
Because Z1 and Z2 are parallel, right? Now the second part is L1 X1 cross, and the force is, let's write from above, it is Fx C2 minus Fy S2 Fx S2 plus Fy C2 and 0, right? So this is, again, just to clarify, this is x, this is y, and this is z, right? And if you take cross product, so again, x and x will be 0, x and z are 0 because this term is 0, so only term will be x cross y, right, which is in z. Okay, so this will be finally equal to, the first term is 0 0 L2 Fy plus, what's it will be, L, so 0 0, and it will be L1 Fx S2 plus L1 Fy C2, right? So finally the joint torque at 1 expressed in frame 1 is 0 0 and L2 Fy plus L1 Fx S2 plus L1 Fy C2. That's it. That's the expression, right? So it's a very systematic approach of doing things, right? And if you, once you understand the process and you know how to, basically, again, what did we do? We started from the end effector and we propagated the forces and torques back to the base, right? So that's what force propagation. And force propagation, again, important point, force propagation we start generally from the end, right, the last link to the first link. And for velocity propagation, we start from the first link to the last link, right, because of convenience. So yeah, so basically that was the goal of this example, to demonstrate how to find out the joint torques and the forces on the links once the end effector force is provided, right? So if we look at this expression now, here we will derive another, that's the last topic for today, that we derive another important relation, just as we did in the last class. So in the last class, we saw that x dot, that is the end effector velocity, is related using to the joint rates using the Jacobian, right? This is what we saw. Okay, now is there a relation between the task space forces, right, that is F, and joint space forces, that are the torques, right? Is there any relation between them? So that's what we'll see right now. Okay, so again, for any, let's say, manipulator, if there is some force F, right, and the position of end effector is x, let's say, right, and when we apply a force, right, there is some displacement of the end effector, let's say by delta x, right? So delta x is displacement of the end effector, right? So what's the work, basically? Work done is force times displacement, right? So F dot delta x, right? This is work done. Now for an ideal system, work done by external force, which is in this case uh, the F on the end effector, is equal to work done by the internal forces, right? So due to this energy conservation law, right, and there is no losses and all, so what is, and so let's say if the end effector displaces by delta x, so the joints also displace slightly, right? So let that be delta theta. No, that is joint angle displacement. Okay, now work done due to joint torques, no, because we are applying a force, so there should be some torque there. Okay, so work due to joint torques is, again, as for linear case, it's force times displacement F dot x. So for torque is tau times the displacement in joint angles, right? And basically the what we have to do is F transpose delta x. By the way, for two vectors, a dot b is same as writing as a transpose b. Just make sure you verify this, convince yourself that this is true, right? So F transpose delta x is tau transpose delta theta, right? Now from kinematic relation, we know that delta x is Jacobian times delta theta, right? We know that, we have seen that. That's the first thing which we derived in the last class, right? So what we can do is rewrite this F delta x is j delta theta is equal to tau times delta theta, right? So delta theta is common both sides, right? So which implies that F transpose j is equal to tau transpose, right? Which implies that taking transpose on both sides, tau is equal to j transpose F, and there we have it, right? That's the relation between joint space forces, or torques as we say, to task space forces. And generally these forces are applied at end effector itself. So it will be the force at the end effector, the Jacobian of the end effector, related to the joint torques of the manipulator, right? So again, a very important relationship. So basically these two relations, which one we saw in the previous class, that the kinematics one, x dot is equal to j theta dot, and the second one, that tau is equal to j transpose F, right? So these are very much important, right? should derive them on your own and verify that they are correct. Okay, any doubts still here?
No, sir.
Okay. So the final thing which we will do is just to verify that indeed this is true, and just to convince ourselves the same thing which we derived here, by the entire calculation. Let's see if we can directly write it using the relation of tau is equal to J transpose F. Okay, so verification of the joint torque relation from the example above. Okay, so what do we have? We need to find this, right, which is tau 1 tau 2, right? And what do we have is we have the force F at the end effector. Okay, now we need to find out J at the Jacobian of the end effector, basically. Okay, so what we can write is, now since tau has only, we know that tau has only components in the z direction, right? So although here we derived them in the first frame or in the second frame, basically those two are the same because the z axis is the same, right? So what we will do is that we will write the entire relation in the second frame itself. So this is fine, this thing. I chose the second frame as my description frame. Okay, and since I could have written in first frame also, then I would have to write forces also in the first frame, right? Because forces, the expression of forces is much simpler, in this frame, second frame. So I chose the second frame, right? So this quantity we know, right? This is given that this is fx, fy and 0, right? So the only quantity that is left to find out is the Jacobian, and important to note, Jacobian expressed in the second frame. So important point, Jacobians are frame dependent, right? I mean, the components of the Jacobian depends on the frame in which the Jacobian is being expressed, right? So that quantity also changes from frame to frame. So in the last class, in the last class we saw for a 2R manipulator that, so there we found out the Jacobian, and that Jacobian was in the base frame, that is in the 0th frame, right? We saw that J0, that is expressed in the 0th frame, it was what? It was, if you remember, we just took derivative of the position of the end effector with respect to the origin, and wrote it in the matrix form. So you can check notes from the previous discussion hour here to verify, or else if you have derived on your own, you would remember this, that this is the Jacobian which we found out, right? And this is the expression of that end effector Jacobian in the base frame, right? So this is in the base frame, right? So to get this, what do we need to do, right? To get the quantity on the left hand side from the quantity on the right hand side, what do we have to add on the right hand side, right? We have to multiply by a suitable rotation matrix, right? Now what is this rotation matrix? So frame 2 is rotated by how much angle? So theta 1 and then theta 2. So theta 1 plus theta 2, that's the rotation angle between frame 0 and frame 2, right? So this quantity is 220 transpose, and 220 we know is cos theta 1 plus theta 2 minus sin theta 1 plus theta 2 sin theta 1 plus theta 2 cos theta 1 plus theta 2, right? And then 0 0 1 0 0. No need to write 3 components itself because we are doing in 2 cases, so just this is enough. And then transpose, right? So transpose of this would be, and just writing that 2 cross 2 components, it will be C12 S12 minus S12 C12, right? So this is the rotation matrix from 0 to 2, right? So the end effector Jacobian in the second frame is by transforming the end effector Jacobian in the 0th frame, right? And this is C12 S12 minus S12 C12, and here we write the Jacobian in the 0th frame, which is L1 S1 minus L2 S12 L1 C1 plus L2 C12 minus L2 S12 L2 C12, right? Now if you multiply, and yeah, it's not a very complicated multiplication. If you multiply and use the basic sin A plus B cos A plus B trigonometric identities, what you will finally get is, I am writing directly, that is L1 S2 0 L1 C2 plus L2 and L2, right? So this is the Jacobian. Okay, Now, what was our initial thing? That tau in two frame is,
Sir,
yeah.
here, while writing this rotation matrix, you told that we will ignore this, the below parts, that is zero
Mm-hmm,
zero one.
mm-hmm, mm-hmm.
You said we'll ignore it, no, sir.
Yeah,
If you, if
yeah.
only if we, yes, sir. You said we ignore it, no, sir.
Yeah, because our Jacobian also we have written in only xy coordinates. So that's why for rotation matrix also I'm just taking xy coordinates corresponding to.
We can do that like that, sir. Like in a matrix, can we just take a selected number of elements and
Yeah, 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 yeah. Like basically, this is the in the, let's say if you are not considering the z axis, then the rotation, and you are just considering the x axis and the y axis, then that's how the x and y will transform. And anyways, because the rotation is about z, so components along z are not changing. So the only components which will change is along x and y. Let's say if the rotation were about y axis, right, then you can selectively take the rows of x and z, and also what you are multiplying it to, there also x and z, and then multiply them. But yeah, if you feel that you should do it properly, you can just take it the full matrix here also, and the Jacobian also you can add zeros, right? So that's why.
yes, sir, I understood. So now I understood.
Yeah.
Yes.
So finally the result will be that the Jacobian in the two frame, the transpose of it into f in the two frame. So basically the transpose of the Jacobian is L1 S2 L1 C2 plus L2 0 L2, right? And the forces are Fx Fy 0, right? So basically the values of the joint torques tau 1 and tau 2, if you multiply, you will get that it's L1 S2 Fx plus L1 C2 Fy plus L2 Fy, and then the second is just L2 Fy, right? And if you compare to the result above, just compare that for 2 it's L2 Fy, and here also for 2 we got L2 Fy, right? For 1 also, if you will compare, it's the exactly the same thing, right? So they are the same, so hence this relation is valid. We have verified for a 2R manipulator in this case, right? So that's the key takeaway from today's discussion are that the forces on the end effector or the forces in the task space are related to the forces in the joint space, or the joint, also called as joint torques. They are also related by Jacobian, right? So these relations ensure that, or it can be concluded from these relations that Jacobian is a very fundamental matrix, in analysis of any robotic system. So computing Jacobians is one of the primary things, or the very first things that we do while analyzing any system. Okay, so yeah, any doubts in this derivation? I think it's I made it pretty much clear in this example.
Sir,
Yeah.
can you just scroll it up to the 2R manipulator, sir?
Mm-hmm.
Uh, yes, sir, yes, sir, yes, sir. Stop here, sir. Yes, sir. Here we have written moment of N1. We have written is N1 is equal to N2 plus that term we have written, sir. Uh, Now I'm asking this conceptually, sir. Um, like in the like when we have applied force F at the end effector, that created a moment in joint 2, and when we are analyzing joint 1, uh, th- th- there is two there are two moments acting in joint one is due to that force F, and one more is due to the joint 2 moment
Right,
due to
right,
joint 2.
right, right.
That's why we wrote this
Yeah,
relation, no, sir.
yeah.
Okay, so joint 1 is experiencing moment also from joint 2 as well.
Yes, yes. You're right.
Okay, yes sir, yes sir.
Okay, so yeah, I will stop here for this discussion hour, right? And in the next discussion hour, we will take up some questions from the previous year assignments and also continue our discussion on the theoretical concepts ahead. So, yeah, in case of any doubts, feel free to post them on the YouTube channel videos. Okay, so, okay, then see you in the next discussion hour.
Thank you, sir. Thank you.
Okay.